Okay. This tutorial 10 has already been shared on your canvas, and I am assuming that you already have a good look at it, right? If you don't, you still have time to look, and of course you should look at this because there are some reactions that can be helpful for us to know exactly how these reactions are occurring and what should we do for this reaction to find out what the reaction is occurring, right? So alkene, let's say we are discussing with the alkene, although we have finished it quite early, the alkene, but later on at this tutorial, we'll see, because the last topic we studied was alcohol, aldehyde, ketones, and all those things. And some of the reactions of the topic that we actually have discussed yesterday is in the lecture slide. So please go and see the lecture slide, even though I did not go through all the reactions one by one, but you should, because the reactions are very well self-explanatory. So I do not have to go through it one by one to tell you what is happening there. If you look at it, you will see what is going on and how should we actually okay, yeah. So how should we actually find out what the product is going to be happen for this type of reactions? One of the earliest reaction that you have seen, that reaction of the alkene, which is when it has a double bond, or alkyne. Mostly we haven't studied the alkyne, but we know what is alkyne, right? When there's a three bonding or unsaturation, double unsaturation, and altogether three bonds, that is the alkyne. And in these reactions, for this type of reactions are very similar. So when alkene is there and you are adding a hydrohalogeno acid, right? So what is going to happen is Markovnikov reactions, right? Markovnikov reaction that tells that the hydrogen is going to go to the carbon that has already a lot of hydrogen there, or rich gets richer, right? So the hydrogen is going to go to this carbon because here there are two hydrogen in this system, in this carbon, but there is iodine, right? There is iodine is going to go there where is less hydrogen. So this product is not highly unlikely that it will occur, but this product will occur because this is following Markovnikov rule. This product can be occur, that can happen if there is an oxidizing agent there. For example, hydrogen peroxide. If in the solution, hydrogen peroxide is as a solution, or permanganate or chlorate ions are there. Okay, so this type of oxidizing agent as a solution, this type of reaction can occur, anti-Markovnikov rule can occur. Okay, so again, this is another type of alkene that is happening when there is a branched chain just adjacent to the double bond. Right, so this double bond is here and the branch chain of carbon is there. So again, the similar thing, both of the reaction possible, but mostly Markovnikov rule will be prevailed, and then this type of reaction will occur. That is here, this type of reaction. This is a very small minor percentage of the compound will be produced. If it is 95%, it will be just 5% of this. So now you already understand that this is a little bit difficult to control this type of reaction. Although we know Markovnikov rule, but it is difficult to control because you are getting a mixture of both of the product, right? This product and this product is different. So their properties or chemical characteristic will be different as well. But you cannot control if you are adding this thing unless you are adding some kind of conditions, right? Unless you are adding some kind of conditions. So only then it will be much more probable to have most of this one type of product in this thing. Sulfonation, how do we add a sulfonic group or SO3 group in this alkene? By the way, we will be learning soon about the. Hold on, let me just adjust the table. It is much better this way. Okay, so I can have space to put papers. All right. So sulfonation. I mean, what do you call it? Okay, so this is, we will be learning about SN1, SN2 later on after we finish this part. So this type of alkene, when there is a double bond and then a chlorine is there, let's say there is one hydrogen only and chlorine here, so it will be vinyl chloride, right? You don't have to remember now. I will be talking it later on, but just for your information, I am just showing one example here. But later I will talk more about the vinyl or aryl or allyl and what is that? It's called alkyl halide later on. Okay. Okay. So for the sulfonation, when sulfuric acid is added to the alkene, the hydrogen atom goes to the carbon and the double bond, and bisulfate ion goes to the other carbon atoms. So this is, it is very obvious that CH2 is there. So there is basically our what basically there is no difference between this carbon, right? There is this, both carbon are the same, similar way, similar look. So if we add sulfuric acid, of course, it will be very strong sulfuric acid, more than 80%. And then ethyl hydrogen sulfate will be produced. So one hydrogen is going to one carbon, another, the rest of these, because sulfuric acid, it will be dissociated or ionized in this form. One is hydrogen and another one is HSO4. So these are the two ways that sulfuric acid is ionized or protonized in the water. It's not the way that two hydrogen and then totally sulfate ion. No, in not that way. It doesn't dissociate in that way. So this is the way sulfuric. So this hydrogen is going to one carbon and then this sulfate, bisulfate ion, going to another carbon. It doesn't matter to this carbon or that carbon, any carbon it can go. But later on, the interesting part is later on when in presence of water or steam, I mean, better to say the steam because it is water and then you are putting heat. So you are putting steam that is already hot water or hot water vapor. It is producing this thing is producing alcohol. This sulfate ion, ethyl hydrogen sulfate, is producing you alcohol, and of course the sulfuric acid. So the interesting thing, can you see that you are adding sulfuric acid to get the sulfuric acid, exactly the same sulfuric acid you're getting back, but in between from there, I mean, in the transition, it is the alkene becomes alcohol. So this is very interesting thing for production of alcohol. This is very interesting, and then it is very useful. Exactly, useful. So that's why sulfuric acid, production of sulfuric acid is very important. And as a chemical engineer student, you later on will be learning that how to produce sulfuric acid from different production channel or production setup, which is the production, or you have to find out the best design to come up with the molding, or not molding, the instrumentation that you produce the sulfuric acid efficiently, less it, because sulfuric acid production it takes a lot of heat. Okay, the another thing, but if it is not the ethylene, if it is another alkene that these carbons are not symmetric on the either side, right? If it's not two folds, if the carbon are not symmetric from the either side, what is happening? So again, the Markovnikov rule. So every time Markovnikov rule we are looking at, but it is for the different composition or different reaction. So we just remember the Markovnikov rule, how it works, but the reactant or the conditions different, right? Here, sulfuric acid, there it was hydrogen iodide or hydrogen chloride or hydrogen bromide, all those things. And then sulfuric acid, it can be other type of acid, nitric acid as well. Nitration is a little bit different because you have seen that nitration, it needs sulfuric acid as well, but it follows the Markovnikov rule as well. So for this case, we see that here it is this carbon, let's say this carbon number 1, carbon number 2, not let's say, we count in this way. So this carbon number 3. So carbon number 2 has less hydrogen, right? Carbon number 2 has less hydrogen. And so the hydrogen is going to, so the sulfur bisulfate ion is going to attach to this carbon, and the hydrogen is going to attach to this carbon. And later on, the same steam you add, you are getting isopropyl alcohol. Okay, not N-propyl alcohol. So if somebody comes up with this idea that CH3 and then CH2 and then CH2OH, it would be wrong. It would be wrong. You will not get this product. You will not get this product. So it is the isopropyl. That means hydroxyl group as the number 2 carbon, not number 1 carbon, right? So this is another thing that we should be considering. If we just add halogen, this is the most easy. It looks most easy reaction, but the problem is it has to be in organic non-polar solvent. Carbon tetrachloride is a non-polar solvent. If it is polar solvent, it is going to produce this hydrogen, hydrohalide, halogenohydride type of product. The hydrogen and halogen both will be there if it is a polar. If it's not polar, then both of the iodine, halogen is going to attach to either side of the hydrogen, because here you cannot differentiate. These two bromine is going to go, of course, so each hydrogen, each carbon, 1 atom each is going to be attached. Interesting thing is this reaction, and is one of the most valuable reaction or most important that you can work with, or you can produce a lot of product. First of thing, that here you are having this reaction, this product. Of course, this is very good that you are getting this product. Why? This product you are getting from the reaction of isopropane, all right? Hold on. Big boss. So isopropane. So in that case, you will see that you are getting the reaction, right? You are getting the reaction, and then you're getting the product of dibromomethane propane, 2-methyl propane, right? Dibromo 1,2-dibromo 2-methyl propane. But it is the final product when there is no carbon, when there is carbon tetrachloride. But if we remove this carbon tetrachloride after we have added this bromine, then we can produce a lot of other products. This is the interesting thing. And if we add iodine, let's say bromine, iodine, all are, I understand that halogen. But if you just add iodine, you are getting the iodine bromo iodo-propane, right? If you add nitrate ion, you are getting the nitro. And if you get water, you are getting alcohol later on. So now I am sure that you're smart enough to understand that this reaction, that number 2 reaction is showing, basically this is the similar thing actually. So it is not the direct product and it is a slow stage. There is something called bromo ion is being formed during the production between these two carbon, where there is a double bond on the other side, right? There is a bromo ion. So this bromo ion is being formed. So how does this product? So here as well, it will produce a bromo ion. Of course, this double bond will be broken. And then this is the intermediate state. It is happening. So double bond is broken. Bromine is going to be attached, right? There's no double bond anymore. So bromine is going to, so it is happening. And then because this bromine, this is the bromine molecule, right? Bromine atom, bromine molecule is 2 atoms. So here it will become, one is positively charged, of course, not positively charged, but slightly positive, slightly negative charge. So this negative charge is going to attach later on here. It will break on, and then this is the product, final product is being produced. So same thing, bromine, when we are attaching here, right? So this bromine positive charge is forming positive charge, and later on, of course, it is bromine cannot have positive charge to is the halogen. It has only one possibility that it can form only one bond, this bond. So it cannot has 2 bonds. It will break down, or it will break 1 bond, and then it is going to form this bond, and carbon will produce a carbocation later on. If this bond is broken, iodine is going to be attached to this carbon, right? So this is how the iodo-bromo propane or isopropane is being formed. Nitrate, similar way, nitrate is already negative, so it will attack to this positive side. And then another thing is water. When you're getting water, water also can produce a what do you call it? Hydroxyl group. Water is producing hydroxyl group. This hydroxyl group is going to get attached to this product. Question is, I mean, the interesting thing is this bromine is always going to attach to this second carbon, not the first carbon. This is the interesting thing, actually, right? So bromine is going to attach to this hydrogen in the middle, because this is in a Markovnikov rule. It would happen that when there is more hydrogen to that carbon, the hydrogen would go to that carbon. Since there is only bromine, still it is going to the less hydrogen, the carbon that is less hydrogen, and this iodo, this nitro, this water, it is not coming along. This iodo group is coming from hydrogen iodide, right? It is coming from hydrogen iodide. So this hydrogen is positively charged and iodine is negatively charged. So this positive charge, there's another bromine which is form a HBr at the end. HBr at the end, right? So HNO3, this is HBr at the end, and this hydrogen is going away from it. Also, it is producing HBr. So this is how the mechanism of the reaction is working. One of the interesting reaction is, this is last 2 reactions. One of the interesting reaction that is occurring is dimerization. Is there any question so far? No question. Okay, if you have any question, just shout out, unmute yourself and talk. I'm not visiting again and again to the chat box. So dimerization. Dimerization, what does this dimerization mean actually? Here, still the alkene, right? The alkene, I have the same compound. If we add sulfuric acid, which we did previously here, sulfonation, this 80% sulfuric acid, and we saw this is the product. This is the simple way of showing what is happening. But if we look into a detail of what is happening actually, they are producing the similar product, but different arrangement. So that is called the dimerization, right? So for this case, sulfuric acid you are adding, and it is producing this type of product. Let me give you a detail of it. And so for sulfuric acid, we are adding, and then sulfuric acid is the oxidizing agent. All right, sulfuric acid is oxidizing agent, and in presence of another molecule that is CH3. Let's say that it is not shown here, but it will be in this way. CH3 here. CH3. If you are wondering that where this whole part is coming from, so this is the another part that has not been shown, and H. So this is isobutane. Okay, this isobutane. All right, so this isobutane is added to this methane, ethane, propane, isopropane, tart butane is added here to this isopropane, and then at 80 degrees centigrade, it is getting dimerized. That means it is getting attached. This part of hydrogen is going, I mean, it is, of course, is going away, and then one bond is formed here. So this bond is being formed to this with this carbon. So this is one of the product. Another way it is forming, this carbon is going to attach to this, I mean, a methyl group, and they are forming another compound. So there are similar thing. Everything is similar, all number of hydrogen, number of carbon, the number of double bonds, all the same number, but the arrangement or the places it is attached is different. So that is called the dimer. This compound number 1 and number 2 are the similar thing. So these are, they are two dimer, but not exactly stereo isomer. They are stereo isomer, but there's not exactly the same thing, right? So they are the dimers. And in presence of nickel, when we do this reduction, that means you add hydrogen to it, reduce it. So of course, this double bond is no more. It is producing alkane. So only one single product. So from this product, this compound or this reactant, you produce only one product, but both ways. There are two possible ways that you can produce. When, how to increase the length. How do we increase the length of the compound, and has a lot of branching on it, a lot of branch. We are adding a lot of branching. Otherwise, you can just add, you can just increase the length of carbon chain. There's carbon, 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 carbon. You can increase the carbon length, no problem. That is not that big issue, but dimerization, when you're adding the branched chain to this, or not that branched chain reactant, it is a difficult, it is different, right? So there is this way we can add the reactant in dimerization. Alkylation as well, this is a similar thing. We see that concentrated sulfuric acid or hydrofluoride fluoric acid, and the similar way we can add this, increase the branched chain alkane to this seemingly linear chain alkanes. So this is the alkylation of the reaction. All right. So how these alkylation reaction occurring? First of all, this hydrogen will go away from this reaction, and then it is giving a positive charge. Right, it is giving a positive charge. If hydrogen goes away, carbon does not have all fluor bonding, so it will produce a cation. It will produce a cation, and this cation is going to be attached to this carbon because this carbon is having a less bonding as well, because here there are a lot of there is a lot of electrons here, double bond. So this carbon is going to get attached to this carbon. So this bond, this is opened up, and then hydrogen is going to attach to this carbon, and this whole branch is attached, will be attaching to this carbon as well. So that is how the bonding is occur. All right. So this is our alkylation, sulfonation, and halogenation, and all those Markovnikov rule that we are adding, sulfonation and alkenes reactions of all those things we have done. And we are now moving to this SN1 and SN2 type of reaction. But for SN1 and SN2 type reaction, I will go to the whiteboard probably, so that, okay, before I go to the whiteboard, I think we can write it here for SN1 and SN2 reaction. Okay. So is there any question? Anybody has any question? No question, yeah? Everything is clear. All right, good. So now for the SN1 and SN2 type of reaction, we will talk first the SN2 reaction. We'll talk first the SN2 reaction, and before that, hello. Hello, sorry, I got disconnected. Okay, so what else then? Okay, so for SN1, SN2 type of mechanism, the reactions that we already have discussed previously in the lecture class, we are going to discuss this thing today as well. I mean, for some of the mechanism, and then the conditions that we should be looking into for this SN1 and SN2 reactions. And before that, actually, let me go through that lecture slide as well. For the last time, and show you why it is important for us to know SN1 and SN2 reactions, how it may help us to choose okay, so here we are, and then Yeah. So for this type, we have seen this before, and then I'm showing it again. That SN2 reaction of a primary and secondary alkyl halide. Primary and secondary, there are two things, right? Primary and secondary. So just remember this thing, that primary and secondary alkyl halide I'm talking about. This primary and secondary alkyl halide. Can anybody tell me what is the primary and what is secondary alkyl halide? Is there any idea? Anybody can tell what is primary, what is secondary alkyl halide? So this is a primary halide. Let's say chloride is here, and this is a secondary alkyl halide when there is chlorine is there. So this carbon, the chlorine is attached. It is attached to another carbon, two carbons. So this is the secondary, this is primary. The chlorine attached to this carbon does only one. It is bonded to only one carbon. That means it is bonded to here, this carbon, only one. And this carbon is bonded to two other carbon. So this is a secondary. This is 2 degree, this is 1 degree. And of course, you understand that if this carbon has bonded to another 3 carbon, then it will be tertiary, right? This is 3 degree, right? So this is, we are for SN1 and SN2, primarily is for first degree and secondary carbon. Halogen, of course, the halogen of alkyl halide, but primary and secondary, SN1, SN2. For third tertiary, SN1 is much more easier or helpful. So when I'm saying that alkyl halide, there are a few reservation with this alkyl halide talking. With that, I'm talking of the alkyl halide. There are a few reservations that we should be discussing about, because phenyl, allyl, all those things. I will not give you the names, but what I will give you is my computer is, I don't know if the system is slow or my computer is slow. Okay, so let's say there is CH3, right? CH3, CH2, and bromine. We will talk mostly about bromine because there are some reason for that I'm going to tell you. So it is having a reaction in, hydroxyl, let's say any hydroxyl base, right? Any hydroxyl base. And let's say it is like 25 degrees, 30 degrees, 40 degrees, around that temperature, 25 degrees centigrade temperature or 40 degrees centigrade. So in this case, we immediately understood that this is the alkyl halide. It is a primary alkyl halide, 1 degree alkyl halide. Hydroxyl is a strong base because it is coming from either sodium hydroxide or potassium hydroxide or lithium hydroxide, whatever. There is a negative charge. It is carrying a negative charge. That means this is quite a strong base, right? And degree centigrade. So this is at 25 degrees centigrade, strong base, 1 degree alkyl halide. So SN2 reaction is very much possible. So what it'll do is this hydroxyl ion, it is coming, let's say this is CH and bromine is here. And this is CH, another CH3 is here, this this. So this is hydrogen and hydrogen. Hydrogen is smaller size, much smaller than CH3. So this hydroxyl group will come from just exactly 180 degrees. So this bromine, it will kick out the bromine. It will not wait for bromine to go by itself. It will force the bromine to go out and produce a product. So this is going to produce CH3, CHH, of course, hydroxyl group, right? And it is producing a halogen, an alcohol in this way. It is producing an alcohol, and this bromine is going away with, I don't know what it came up with. It's either it came up with sodium or potassium or lithium. It is producing a sodium or potassium or lithium bromide. In this way, this is the formation is happening. So now another thing, if it is a double bond, benzene ring, it's a benzene ring, and there is a CH3, no, sorry, it should be CH2, and there is CH2 and bromine, right? So if I add hydroxyl ion, or let's say not hydroxyl, hydroxyl has many. So another strong base, alkoxy ion, CH3O, methyl. What is the name of this? Methoxy ion, yes. This is a methoxy ion. So if methoxy or ethoxy also could be CH3, CH2, negative charge. So this is ethoxy, either methoxy or ethoxy, or hydroxy, right? Hydroxy, I have already said, that's why I'm not taking this time. So in this case, and let's say it is 40 degrees centigrade, or let's say it's 50 degrees centigrade, right? Around 40, 50 degrees centigrade, just a little above from the room temperature. Room temperature in some countries is already 35-degree room temperature, right? So a little bit higher than the room temperature. The reaction is occurring is SN2. This will be SN2 reaction. Again, so this methoxy is going to, this bromine will be kicked out. I don't know, it's a good, probably it's a strong word, but it will force this bromine to go out from this thing, and then it will have the reaction, of course, similar way. So in this case, what is the reaction is occurring? What is the product is being formed? The product is, this reaction, it has no effect on this benzene ring itself. Benzene, we have seen the very beginning of the organic chemistry that benzene is quite stable, right? Because of this resonance, benzene is quite stable. Nonetheless, it does reaction, it go under reaction, but is to some extent it is stable. So this CH2 and then CH and OCH3. So this will be the product. Of course, this is CH2. So this will be the product. So it is an ether. It is an ether is being produced in this way, right? So yeah, now another thing interesting, just remember this thing. I am producing it here, and this is bromine, right? This is bromine, right? So can it be, can I produce a reaction from here? We cannot produce a reaction from here because it is an aryl halide. If this halogen ring is directly attached to the carbon of the benzene ring, for this case, we see that this bromine is not directly attached to the this aromatic ring, right? It's not directly attached to this benzene. There is a chain or branch attached to it, and then this bromine is attached. If the bromine were attached to this carbon, the reaction was still possible. But when this bromine is directly attached to this main structure of this aromatic ring, this reaction, not SN1, not SN2, not elimination, is not possible. Okay, it is not possible. Simply, just remember that if the bromine, not only bromine, and halogen is attached directly to the carbon, this is also halide, it is SN1, SN2 or elimination reaction is not possible. Okay, so another thing, another non-possible way is that if CH2, right, CH2 and no, CH2, not CH2, it's CH3 here and CH2 here, and then this is CHBr. In this type of reactant, when this bromine is directly attached to this alkyl halide, but it is a double bond, this carbon is attached to the double bond, and this bromine or iodine or fluorine or chlorine, whatever attached to this carbon, this also does not go for reaction. So this is allylic halide, allyl halide, it's called allyl, it's called aryl, it's called aryl. It's called aryl, it's allyl. So these two reactions are not possible. But if let's say that, let me delete this thing. Let's say this this bromine is not directly attached to here, but to the next carbon, then it would be possible. CH here, and then again CH2, and then Br. So this reaction would be possible for this case because this bromine is not directly attached to this double bond carbon. So this time, I mean, for this type of reactant, SN2 or SN1 would be possible, right? So this is another thing that we should be considering it. All right, so now I want to move to a new page, but I do not have any page here. What should I do? Should I delete this thing? Do you think that I can delete? Is that okay for you that I delete? Hello? You guys are not listening or what? Don't want to delete here. So I go to another, look for another, hold on, just 1 minute. Okay, so I got another fine white page. I'm sure that you can see, hopefully. So for here, I'm going for another SN1, so SN2 reaction you have seen. So what the condition is, it should be linear. It shouldn't be only 1 or 2nd degree alkyl halide. It should be alkyl halide is not aryl halide or allyl. It should be vinyl halide or benzyl. That means it is not directly attached to this benzene ring, or it is not directly attached to the carbon, which is a part of the double bond, right? So that would be SN1, SN2 reaction, SN2 reaction. For SN, how to choose whether it will be SN1 or SN2. First of all, okay, before that, I go to the same thing here. So we know that in this case, there is no option for SN1 or SN2 if it is aryl or allyl. That means if the bromine is directly attached to this benzene ring, there will be no reaction of SN1. If the bromine or iodine or chlorine is directly attached to the double bond, whether it is a benzene ring or not, if it's double bond directly attached, it will not be possible for SN or SN2 reaction. So these two are out of question or consideration. So now we'll talk more about the SN1, SN2. So SN2 reaction will occur if there is a strong base and not that high temperature. And of course, it should be not that branched. So it is 1 degree alcohol halogen, alkyl halide, or 2 degree also possible sometimes if the base is very strong. Otherwise, probably it will be SN1. So what are the things that consideration? That is already have seen number 1. It should be 1 degree or sometimes 2 degree alkyl halide so that it is SN2 reaction, right? If it is 3 degree alkyl halide, then it should be SN1 reaction. What SN1 reaction we will come later on to say. So now, consideration number 2, if it is the leaving group, right? For SN1 reaction, it was bromine. The leaving group was bromine. If the leaving group is stable, it is not that reactive, then SN2 reaction is preferable. It should be SN2 reaction. For example, that's why we are showing bromine. Bromine is quite bigger than chlorine. Chlorine is smaller than bromine. And of course, iodine is even bigger, right? The atomic size. And chlorine has a negative charge on it. Bromine also has a negative charge. Iodine, so does the iodine. For a smaller charge of chlorine, the negative charge is small and then it's compact. It's compact, and then this small charge, you can, if you look at it, since it is smaller, you can see that negative charge, the ratio to the atomic size of negative, no matter what, 1 charge or 2 charge, since it is small, the ratio, the percentage is bigger, right? Compared to the size. The same number of charge compared to the size of bromine is less. So that means chlorine will be much more reactive than bromine. Of course, iodine is better because it's bigger. The charge is all over. It is dispersed. Charge is dispersed all over. So for the bigger molecule, so that is much stable. It's kind of, you can think of, it's not resonance. There's no resonance happening, but you can see that the charge is being delocalized. It is not exactly to one position and then it is very active. It is being delocalized, so charge is going all over. So it has a little time for it to be stabilized. And that is why if the leaving group is better or bigger, or the charge is not very strong, strongly charge is not very strongly localized or very active, then it is a better. So SN2 reaction is possible. SN2 reaction will be possible for this type of reaction, for this type of product. But if the leaving group is very strong, let's say that you are removing a hydroxyl ion. Was something hydroxy it was attached to this, not necessarily alkyl halide, but hydroxy it can be. So if it was hydroxy, it is very important. Almost is very hard because hydroxy is a very strong base and it will be very reactive. So SN2 reaction will not be possible for it. SN1 reaction rather it will be possible because hydroxy ion, nobody can come and then throw hydroxy out. It is strong base, charge is localized, and it does not want to leave. So the nucleophile that is coming to attack here, it will have to wait for this hydroxyl to go out to produce an intermediate cationic state where this nucleophile later on can go and attack. So this thing will be SN1 type reaction. SN1 type reaction will be SN1 type of reaction. All right. Okay, so steric hindrance that we have already seen, or we have already seen for the main substrate, that means the main product that is nucleophile is going to attack. If the steric substrate hindrance for the attacker, now the attacker, right? Steric hindrance for the attacker by the nucleophile. That is nucleophile and then substrate. So if the steric hindrance for the nucleophile is very small, right? Is not much hindrance, so that it will be much more favorable to SN2 reaction. But if it is quite steric, I mean, hindrance is bigger, then it will be SN1 reaction. So nucleophile, let's say that we have seen that hydroxyl ion is going to attack the nucleophile attack, or ethoxy ion. In the last slide, we have seen ethoxy ion, O negative, or methoxy ion. There is strong bases, right? It's a strong base, so they are going to attack as a nucleophile. Number one, I mean, for this hydroxyl, we have seen it is very small size, right? So small sizes can come and then attack. So SN2 is very much possible for it. It is very easier for 2 to SN2. But for this CH3CH2O, it is quite big molecule. Although it is a strong base, but it is big molecule. So if you do not provide 1 degree substrate, right? If you do not provide 1 degree substrate and less temperature, then ethoxy ion as a nucleophilic reaction, it will mostly go to an SN1 reaction. Probably it will go to SN1 reaction because the steric hindrance between it within itself is quite big. How it looks like, because we have seen the CH3, CH2, and then it is OH, so hydrogen is here. This is quite big molecule. So this hydrogen and this hydrogen in between them, they have an effect between them, right? They have a hindrance between them, much more than the hydroxyl itself, or this hydrogen has a hindrance between them. So much more than hydroxyl. So this will have a better hydroxyl, I mean, hindrance between them, higher hindrance. So SN2 is SN1 is much, even elimination is much more preferable. So elimination, okay, I'll come to the elimination, but if we understand SN1 and SN2, the elimination is easier. Yeah.
So, are you sharing another screen? Because we only see the one you we see only like black screen. Are you sharing the slide? Are you sharing the slide right now? Because we cannot see.
I'm not sharing the slide. I'm sharing the PDF file that I'm writing on.
Oh,
can you see? You cannot see?
Oh, now can see. Now I can see that.
Huh?
Can.
Can you see?
Now can.
Sorry, yes or no?
Yes.
Okay, good. So, what I'm doing, I was telling that, okay, yeah. Now, okay, so this is another condition that SN1 or SN2 type of reaction will occur, right? Whether SN1 or whether SN2 type of reaction will occur. So if the steric hindrance on the nucleophile is bigger or more hindrance between them happening, so probably SN1 preferable first. Second, probably it will go to the elimination type of reaction. So now I'm coming to the elimination reaction. Before I jump into the elimination reaction, just another condition that I'm going to tell you that if the nucleophile, right, this type of nucleophile, those are coming to attack. If they are very smaller, again, they're very smaller and localized charged. So they, I mean, for example, let's say it's better to give examples than just giving theories. Like consider the halogen are attacker now. It's not a living group, but a halogen attacker, because there can be a lot of different type of nucleophile and attacker, and a lot of different types of things can be a living group, because we have just seen from the lecture slide that a lot of different type of products can be produced through this SN1, SN2 type of reaction. So let's say that fluorine, bromine, or iodine, right? Fluorine is always an exception, but I'm just keeping it here just to make so that probably it will be easier for you to understand better. So when you go down the periodic table, fluorine is smallest size, atomic size, and iodine is the biggest atomic size, right? So here, if I am using this is as a nucleophile, that means they are coming to attack, not a living group, but an attacking group. SN1, SN2 reaction. I do not know whether SN1 or SN2 will happen, but I am adding it as a nucleophile to attack the alkyl hydroxy group, or let's say this is a group that will be removed from here, right? So this fluorine, chlorine, bromine, or come to attack to this carbon, let's say. So what will happen? And this thing I'm fluorine, chlorine, bromine, iodine we will be using in presence of a solvent. Of course, there will be a solvent. We have already seen from the yesterday class or day before yesterday class that protic solvent, polar protic solvent is very bad for SN2 reaction, right? Polar protic solvent will be very bad for SN2 type of reaction. So SN1 type of reaction will be favored if I am adding polar protic solvent in this case, right? So polar protic solvent, PROTIC, protic solvent, okay? If I am adding polar protic solvent, for example, polar protic is HCl, right? It is a polar solvent, of course, hydrogen and chloride. It will be divided in polar, and also it is creating, I mean, it is giving the proton to this solvent. This solvent is having a lot of proton or just water or sulfuric acid or any other acidic medium. This reaction is occurring. So that means this solvent has a lot of proton and it is polar. So this case, fluorine will be much more favored in this type of reaction. And then it is SN1 type of reaction is much more favorable than SN2, because we have already seen this polar protic is bad for SN2 reaction. So this will be SN1 type of reaction. Should I write it here? SN1. This is SN1 type of reaction better. But if it is the polar aprotic, right? Polar aprotic. Oh, sorry. Polar protic. So iodine will be much more favored than chlorine, or iodine will have a much more impact on having that reaction, right? then bromine, then iodine, because polar protic means hydrogen is there. Hydrogen is there, so it will have an induction effect with the smallest charge. So they will have a little bit, crony, little bit association between them because both of them are smaller. So they will try not to go there and attack. They will be very comfortable not to attack. They will sit together because hydrogen, a lot of hydrogen is there. You can ask that why iodine is not having that comfortable effect. Yes, iodine will also have, but iodine is bigger, so it is not having that much attractive force with hydrogen. It is still having attraction force, but it can break that bond as well. So that is why hydrogen is going to attack much faster, right? But if it is a polar aprotic, then fluorine will be much more reactive than any other else. So fluorine in this case has to go find someone to go and attach to become, because fluorine is so reactive, it cannot stay together alone. So in this case, if it is aprotic, SN2 reaction is very good. But polar protic, SN1 reaction will be very good, where iodine will have a better reaction, or will be using as a better nucleophile. Right. Okay, so another thing is elimination reaction 1, elimination reaction 2. Same thing is happening. SN1 or SN2, but the condition are same. Only if the temperature is higher, elimination reaction is occurring. If the temperature is higher, elimination reaction 1 or elimination reaction 2 is occurring based on the condition whether the reaction would go for SN2 or SN1. If the condition is same for SN2 reaction, but the temperature is high, it is going for elimination 2 reaction, E2 reaction. All right. If the condition was very good for SN1 type of reaction and the temperature is suddenly high, it is going for elimination 1 type of reaction. Right. So let's just give a practical example. I think I have already given a practical example previously, and here another one. So this is benzene, not benzene. This has been, oh my God, my battery is dying. Okay, so this is benzene and then CH2Br. Let's say CH2Br is there. And I am adding a hydrogen hydroxyl ion, right? So what is happening is, first this hydroxyl ion, because it is very strong base, so there is this carbon having been bonded 4 bonds, should draw in this way actually, hydrogen here 1, hydrogen there 1, and remove this hydrogen from here. Oh. Right, so this is bromine is also bonded. So what is happening is bromine is already a good living group, right? Bromine is a good living group because bromine is bigger than chlorine. Of course, from fluorine we are not talking about, but from chlorine, bromine is even bigger. If there was the iodine, it was much bigger. It was much easier for it to be removed, because this electron, with what it is taking to itself, it can be localized on itself, right? And then when it is going away, it becomes negatively charged, but carbon will be positively charged. It is not exactly going right now, but because of this strong negative charge, when it is insinuating this carbon, this bromine feels there is no other choice, but the carbon has to release bromine because carbon cannot have more 5 bonds. So it is getting insinuated from this hydroxyl ion. because hydroxyl is strong. And then in this case, bromine hydroxyl is kind of attaching, is not 100% attached, but feeling attraction. And bromine, although it is attached directly, but it is also feeling kind of attaching, going, releasing. So there is no perfect bond between any of them, right? So in that case, the next step, hydrogen is forming a bond and bromine is going away with whatever, maybe sodium or potassium, whatever. This is the reaction, SN2 reaction. But in this case, if I would a high heat, let's say 120 degrees centigrade, right? 120 degrees centigrade. So then it would be elimination reaction. It would be elimination reaction. But for this case, elimination reaction, I will not show for this specific case. I will show for this case, because there is something I'm going to ask you to do. Battery saver, I have to find a source for electricity, right? Okay, so in this case, if I were using a high heat and the compound was like this, CH2CH2Br. So this is a propyl bromide, right? So in this case, hydroxyl ion we are adding, and with high heat, let's say more than 100 degrees centigrade, I'm adding. So what will happen is CH3 and then CH double bond CH2. So the bromine is leaving, of course, elimination. So this hydroxyl ion that it came up with, let's say this hydroxyl ion came up with sodium hydroxide, right? We added sodium because it's hydroxyl ion. So sodium was another thing, or potassium, or lithium, or whatever you think, right? It's a strong base it came up with. So since it's strong heat, we are adding this hydroxyl is going with the sodium bromide is, sorry, this bromine is going with sodium, that is sodium bromide is formed. And then there's one hydrogen is taken away from there and it is producing water of this hydroxyl ion is taking away. So sodium bromide and water. So this is elimination reaction. It is totally producing alkene from there by removing one hydrogen from the system or from the molecule. So this is elimination E2 reaction. This is of course E2 reaction. It was possible for E1, SN2 reaction, but since because of the heat, it becomes elimination 2 instead of SN2, right? So now we will be looking at a, sorry, we will be looking at a SN1 reaction. Let's say this is a tertiary alkyl halide, bromine, and we are adding a base, let's say that is a methanol. methanol, it is not a strong base, but it is base to some extent because it can produce a methoxy ion, but there is hydroxyl ion as hydrogen ion as well. That's why it is not a strong base, right? So what is happening? First of all, it is tertiary alkyl halide, 3 degree, and then it's weaker base. So of course there is no other chance but to have a SN1 type of reaction. SN1 type of reaction means this bromine will go away first. It is also big molecule. It's not like hydroxyl ion. It is a big one, CH3O. It is producing CH3O, but we are not writing it CH3O because there is a hydrogen ion in presence. So it does not dissociate 100% or to give methoxy ion. So this is a bigger one. And then this bromine is going, it will wait. It cannot just come and attack from behind. It does not need to come and attack from behind, first of all. Oh, I forgot to mention. So there is only one possible mixture, right? This is coming to attack from behind of these or 180 degree where this bromine is attached to. So only one type of product will be produced. But for this case, this bromine is going away first. Bromine is going away first, and then this carbon here, it is having a positive charge because bromine has gone. It will wait for the bromine to go. The bromine has a negative charge, hydrogen is a positive charge, so this bond is broken, bromine is going away, and then this methoxy, alcohol, which is at the end is methoxy ion, but is weaker. So it is coming to attack from either side, is from the same position where the bromine was attached to, or from the behind. The bromine just left. So it can come and attack from any side and produce this product again. So this is SN1 reaction. But in this case, if I would add a heat, a strong heat, that means 100, 120 degrees centigrade, it would produce a double bond to this, let's say, double bond to this CH2. And of course, there will be CH3 in this position. So in this way, it would also produce an alkene by eliminating one hydrogen and the bromine, both. So this would be SN1 reaction in presence of higher heat. Right. So one thing I want to ask you to do is for E2 reaction. For E2 reaction. Okay, I want to remove all those things first, delete or erase actually. It's difficult, yeah. Do you have any question? Do I write here or on the board? Which one is better? If I write on the board, can you see? It's difficult to clean up all those things. By the way, there are few tutorials with the good graphics on YouTube for SN1, SN2. You can refer to, and that should be good. But do not need to believe or everything. Or no, I mean, you can, but it is always good to go to the book because book is much more accurate than anyone else talking, even myself. So for E2 reaction, I just want to show you one thing that this is a structure of CH2 double bond CHBr, right? So this Br, right? So I am adding potassium hydroxide, let's say potassium hydroxide or sodium hydroxide or any other hydroxide strong base at 200 degrees centigrade. I'm adding 200 degrees centigrade. I mean using 200 degrees centigrade. So what will happen is, it is, tell me, it is an SN1 or SN2 reaction? SN1 or SN2 reaction? Board no clear. No, sir. There. Okay. Okay. I'm not writing on the board. Okay. So oh, can I open new page from this PDF? I do not know if I can open a new page in PDF. Okay. Can anybody tell me what type of reaction is going to occur? Board not clear. Okay, so I'm not writing on the board, but here. I think the board is disturbing, right? I should turn off. Okay, so can anybody answer me what type of reaction are we expecting? SN1 or SN2? Or elimination 1 or elimination 2? Hello. What type of? Okay, you will not talk anyway. So this is 200 degrees centigrade, potassium hydroxide, strong base we are adding. So 200 degrees centigrade, that means it will be SN2 type of reaction, right? SN2 type of reaction. So SN2 type of elimination type of reaction. So if elimination reaction, what is going to happen is one more unsaturation is going to be occurring. CH, right? Triple bond CH, right? So this is elimination. Oh no, this hydrogen will not be there. Oh my. I made a 5 bonding for this carbon. See, gone, everything. Oh, okay, so this is CH3. So this is an elimination reaction. And of course, potassium hydroxide and water will be there. Another example for elimination reaction that is quite interesting. That C double bond C. No, it's not double bond, it's single bond. C, and then so there are 2 phenyl group and there are 2 bromine group are attached. Can you tell me the name for this molecule? Can you tell me the name of this molecule? Your Menti quiz, last ever Menti quiz for your chemistry class ever you will take for your chemical engineering. There is no more chemical engineering, chemistry. Counting once. Okay, I'll give you 30 seconds to think. 30 seconds to think. To some extent, this online class makes me feel like I'm talking to a world and nobody listening. 2 benzene, 2 phenyl, right? Yes. 2 benzenes, 2 phenyl. Ezra, are you there? Let me disturb you for the last time. Ezra, you're not there. Okay. Chewencom, are you there? Iman? Good. You guys are there, so are you guys chit-chatting like you do in the class? Oh, it's good. Lai, are you there? Okay, so what is the name of this compound? The root is methane ethane, right? So diphenyl dibromoethane. All right. Okay, so this compound, if I am adding the same condition here, right? I'm adding the same condition and in presence of ethanol as a solvent. Ethanol is a solvent, that means ethanol is aprotic. Ethanol is aprotic. Ethanol is not strong, it's not an acid, HCl. So it is good for SN2 reaction. Since it is aprotic, but it is polar. Ethanol is polar but aprotic. So it is good for SN2 reaction. Now it's 200 degrees centigrade. So what will happen is this. Carbon, and then mistake already. Okay, so this is the compound that is being formed. So this is 67% of the compound is being formed. 67% of the compound is being formed. And then what is the rest? There is still SN1, SN2 type reactions going on, a little bit of it. 30%. Or yeah, 33% of SN1 to SN2 type of reaction is going on, although it's high temperature. So mostly it is elimination, a little bit of substitution reaction is going on. But one thing that I want to stress on, that this is alpha carbon. Let's say it's alpha carbon. or number 1 carbon, and this is beta carbon. Just for numbering case, there is no difference in alpha. I mean, for this carbon, there is no alpha, no beta, nothing, all carbon. But just for the sake of understanding which carbon is where, we are numbering it 1, 2, or maybe you can say alpha and beta. Alpha is where this removing the group that is going out is being attached to. So interesting factor is this beta carbon is having the best impact, or it is having the most out of the impact it has to absorb. That means the hydrogen is going away from the beta carbon. Hydrogen is going away from the beta carbon. Same is going for here. In this case, anyone is alpha, anyone is beta. Both are alpha, both are beta, right? So this hydrogen is going out from both of them. So this is an interesting thing about this elimination reaction for E2 reaction for this alpha beta. Now, as I mentioned earlier at the start of this thing, that aryl halide will not go for this elimination reaction or SN2 reaction. Aryl halide means the halogen directly attached to this phenyl group, right? To this benzene ring, directly attached. It is not on a branched chain. There is no CH2 attached to this. Is this bromine, or let's say iodine or chlorine, is directly attached to this. So why it does not do SN1, SN2, or elimination 1, elimination 2 reaction? SN2, right? Or E1 or E2. Why it does not do this? Interesting thing. Why it doesn't do? The reason is here. I'm showing you that, let's say, no, not this way. This is the last thing that I'll be discussing, I think. Yeah, so I will. Is there anything else that I need to discuss? There are something, but okay, no, anyway. So this is, let's say that I'm writing it CH. This phenyl bromide. Why phenyl bromide does not have elimination or SN1, SN2 reaction? So we can write this as this, that it is CH here, CH here, this is bromine, then CH and CH, right? This is a hydrogen, right? So this is, of course, and then where do you want to put the double bond? Here one, and here is another one, double bond, right? So you see that all the carbon has 4 bonds attached to it. Now, which one is alpha, which one is beta? Of course, this one will be the alpha because the bromine is directly attached, and this is beta. Or this could be beta as well. If say that, who else is here? Let's say, or this say, no, I don't agree that this is beta. I say that one is beta. Okay. Or let's say who? Gabriel say, no, I don't agree. That is beta. This is beta. Fair enough. Both sides can be beta. So what is happening is, for the elimination reaction, should I, okay, for elimination first. For the elimination reaction, you add potassium hydroxide, strong base, and then 200 degrees centigrade. Doesn't matter, 250 also can, no problem. There will be no reaction. So why it is non-reaction? The thing is, the hydrogen is going to go away from the beta carbon, right? We have seen this beta carbon, the hydrogen is going away. So from these or these, you consider any of them is beta. So what is happening is carbon, 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 carbon. Right. So of course this is carbon. The bromine is going away. Let's say that the bromine will go away, of course, right? So this hydrogen, there is already one bond here, another one bond here, another one bond, double bond is here. And this is hydrogen, this is hydrogen, this is hydrogen, these three. So, and let's say we consider this one is the beta, right? So there will be hydrogen here. So what is happening is this carbon, since the bromine go away, it will make a bonding double bond. It should has to make a double bond here with this carbon. And this hydrogen, since it goes away from here, it is now 3 bond. It has to make another bond here. It will have to make 4 bond each. So if I make this 4 bond, this carbon has already 4 bond. This carbon already has 4 bond. But the problem is this carbon, the next to beta is, it will not allow this 4 bond. It cannot make 5 bonds. And there is no other way that you can make 4 bond to this beta or this one, either beta, without disturbing the next carbon. So next carbon will have to remove this hydrogen to some extent, anyway, and then has to provide these 4 bonds, which is very unlikely. This bond, if even this hydrogen, first of all, this hydrogen will be very hard to remove because it's already stable structure. And then if it is even removed, this double bond, double bond, double bond, double bond, it is very unlikely. And then the structure will be so rigid, double bond, so rigid, so hard that it will not stay there. So that is why this aryl halide will not have the SN1 elimination reaction. Why it will not have the SN2 reaction? Why it will not have the SN2 reaction? What is the mechanism that it does not have the SN2 reaction? So let's say that we are adding potassium hydroxide, not 200 degrees centigrade, just 25 degrees centigrade, right? And then we are in presence of ethanol. Ethanol is aprotic. Ethanol is aprotic and it is polar. Aprotic and polar. So it doesn't matter. It is very good for SN2. The condition is very good for SN2 reaction, right? Can you tell me one thing? That what is the important phenomena SN2 reaction occurs? What is the stereoisomer type of thing that SN2 reaction, signature for SN2 reaction? What is that? Can anybody tell me? Not much time, so push you, but we know that the attacker, that hydroxyl, from this potassium hydroxide, of course, strong base, so it will produce all hydroxyl. This hydroxyl will go and attack this carbon where bromine is attached from the behind, or 180 degree from behind, right? So it will come and attack 180 degree from behind. If you want to make it 180 degree through the, I didn't bring the model today, but through the behind model, you can imagine, right? There is no way. This carbon, it cannot penetrate through this carbon, and then go and attack this carbon. Or if this mold has to be a little bit distorted to make a way for this hydroxyl to come and attack 100 degree, 80 degrees from it, the mold will break. The structure will break. Because there is no way that you can come around just exactly 180 degrees, just exactly behind the bromine and attack this carbon. There's no way. And that is why There is no SN2 reaction possible for this aryl halide, right? For aryl halide, it's not possible for SN2 or SE2 reaction. Same other thing for SN1 and E2. But another thing is why vinyl one is not having the problem. Why vinyl one is not going through the problem. I mean, going to have this type of reaction. Why it does not occur this type of reaction for vinyl one when the double bond, I mean, bromine is attached directly to the carbon, which is because of this hybridization. This is sp2 hybridization here. If this bromine has to come, then it will produce a carbocation first, which will produce it sp hybridization. So from this sp2 to sp hybridization, the changes in this hybridization, it takes a lot of energy, around 20 more than 20 kilojoule per mole of energy. That is quite much for considering one molecule. That is quite much of energy it needs to distort itself, right? From just it was there and then turn like this. It is difficult for them. And that is why it is not. But I don't want to discuss more and there is no time. But we know that aryl halide, it will not go for SN2 or elimination reaction because of this problem, alpha beta problem, and also it cannot react from behind. So if this type of, so you understand that this is interesting and this is quite helpful for us, the information that SN1, I mean SN2 or elimination reaction doesn't occur for this type of compound. So all the best. And I'm stopping recording here so that later on, if you want to look at it for reference, you can.